Good morning, everyone. Welcome to my presentation. And in the beginning, I would extend my gratitude to my supervisor, Dr. Wahab Hamou-Lhadj, and also my community members, Dr. Liu and Dr. Youssef. And I know in this period, your presence means a lot to me. Thank you again for your support. First of all, I would like to start with the overview of my presentation. In the beginning, I will share the concept of log in the Android development. Then I will move to the research objective and explain what I did. Next, I will review the related studies. This is the current research.
Then I will explain MobiLogLeak approach in 3 steps: reverse engineering, TensorFlow analysis, and context statistics. After it, I will show you the evaluation of this approach. And in the conclusion, I will talk about our finding and also the future work. So let's move to the first step, the context.
During software engineering development, it always works on the debugging, fault analysis, performance diagnosis, and security. However, the practice of logging is ad hoc with no recognized guidelines, which undermine the applications of the logs. In particular, the poor logging practice may cause system vulnerabilities and data breaches, especially in the Android applications. Here is one example. So it's one Java code sniper, and we can say in these functions, and under the condition user is online, there exists one log statement. It has a username and with variables custom name, plus login from, and here is one object and its member function get IP. In the terminal, we will say the date, the time, username, and someone log in from the IP address. If we look at this log statement, we can find it has 4 components. First, it's a login object. It's from the Android API. Next is the member function, and we call them the verbosity levels. In this case, it's info, and we still have the warn, error, debug, and extra. Inside this log statement, it has a static test, which shows the information to help the developers understand the meaning of this message. And also, it has a dynamic content, the custom name, and the location get IP. It can be one variable and also can be one function. If we compare these 4 components, the dynamic content is important because it's related to the user data. However, if we think if this data is sensitive or private, like the social insurance number,
that will cause data leakage problem. So my research objective is explore the impact of logging practice on data leakage of such sensitive information. We investigate
why the log insert into an application can lead to the security vulnerabilities that may be exploited by hacker to obtain these sensitive data. Before I start this work, I would like to check the current research in this field. What I found is there exist many studies that focus on understanding the practice of logging in general stream software development, and they focus on the quality of logs, and also where to log and how to log. For example, Chen and his group conducted one study focusing on the Java system. They examined the logging practice in 21 Java projects from the Apache Software Foundation. Another group, Zheng, they did similar work, but their research their data set is different. They focus on the 1,444 open source mobile apps from the F-Droid repository. And for the quality of log, Chen and his group, identified the login anti-patterns. In addition, Fu and his group run their study with Microsoft developers to investigate where the software developers put the log statement in the industrial system. After I looked through this related studies, they did a really excellent job, but it's not enough. Log can be misused, yielding the security problems. To our knowledge, there is no studies that examine the interplay between the logging, security, and the data privacy. So that's why I started this research. So next, I would like to explain the MobiLogLeak approach. We use the Android apps as our dataset. The first step, we convert this APK to Jimpo code using Suite. Then we will apply the TensorFlow analysis on this Jimpo code. After it, we generate the source sync log-related path. And after we get this path, we did two work. First, we did the context statistics to understand the code structure of this log statement. In another work, we categorize the data leakage type. We check what kind of information may be leaked through this log statement. And next, I will explain this step one by one. So in the first step, we use a reverse engineer APK into the Jimpo code using Suite. We don't assume the availability of the app source code because we find the most of the mobile apps, they are not open source. Then we use Suite to reverse engineer an Android APK. Here is one example between the Java code and the Jimpo code. What we can see is the result is represented as Jimpo code, which contains the original functions like here, and also the variables values name and the types static int. Even though the Jimpo code is a little complex to read, but it can also show us the process of this function. For example, in the Java code, they use while to do the loop, and in the Jimpo code, they use goto. When they calculate the values, they go to label 1 and return go to label 0 to achieve the loop. After we get this Jimpo code, we apply the TensorFlow analysis. So what's the meaning of the TensorFlow analysis? If we look at this data flow graph, each node can be represented as a component. It can be the class or can be one function. And in the node 2, there is one variable which carries the user information or data in the system. And this variable is transferred between the functions from the function node 2 to node 4 until node 7. In the node 7, if there exists one statement, log statement, which prints the value out, we take the path node 2, node 4 to node 7, and this path we consider them as the TensorFlow path. And the TensorFlow analysis is try to get all the paths like this in the Android application. To help understand, we have the one example here. First, in the function belong A, there exists one statement, log statement, which contains the variable $3. So we would like to check the content of $3. We find it's from the function string A. So we went to the function string A and check the return value. The return value is $1, and we check the definition of $1. We find the value is come from this function string E. And we go deep and check the value of the function string E. We find here the return value is $4. Inside this statement, we find this value is come from the database, and it has two functions, one named getString, another named getClone index. To confirm the meaning of these two functions, we went to the Android developer API to check that. In our case, the first parameter is password. So when the getClone index receives the password content, it will return the clone index of the password. And if we give this index to the next function getString, in the final, it will return the value of that clone as a string. So these two functions will take the password value from the database and give the result to the $R4. And the password value will transfer between $R4 to $R1 and until $3. Then in the end, the log statement will print the password value. So here is the 10th floor pass. In our case, it's the password value is print by log. However, it also can be sent by HTTP to some website or to some place, and it also can be written down to some document. However, my work only focuses on the log, so we did the next step, extracting the source sync log related path. Before I did this work, I checked the previous research how they filter the log statement. Normally, they use regular expressions. That means they check this statement contains log, trace, logger, verbose, or info. But it has some limitations because if they check if the statement contains log or not, there are some exceptions like login or dialog. This statements they are not related to log, but they have these letters. So that's why they don't have the 100% accuracy for that. Luckily, in our work, the Jimpo code not only contains the log, but it also contains the log library class, Android utils log. So if we check the regulation expression Android utils log int, so we can 100% confirm all our paths are log related. After I get this path out, we did the first work is understanding the code structure. So in the application levels, we calculate the log density, and we go deep and check the class. We check which component it belongs to. We have the activity service, broadcast provider, and the container receiver. We have the suit method. Well, we check this method is reflective cause or not, and we also check the block they are in the exception or not. Here is one examples. Examples of the Jimpo code, and we can directly see the class name, the function name, and inside the label 29 there is one log statement. So we take this statement out and build the graph. So obviously we see the function name is on preview frame and the class name is like this. And we use our technique to check it's in the final exception. Then we can also check it's in the activity component. Here is in the code level. And in the application level, because we have the application ID and we have the package name, so we can confirm the APK name. Then we went to the Google Play Store and check how many installation it has and what categories it is. The next step, we categorize of the data leakage types. Based on the analysis on the data and Android API, we group the types of data leakage in 4 categories. For the network, it includes the IP, MAC address, device ID. For the location, it includes the longitude, it has the username, user profile, and the token. And for the database, it includes password, email, and the website. After we build the MobiLogLeak approach, we apply it in our experiments. When analyzed 5,000 apps published in 2017 and 2018, and all these apps are selected randomly from Amr Youssef. Amr Youssef is a growing collection of Android apps collected for several resources. And the main resources is the Google Play app market. And these apps, they are from different categories, including the entertainment, business, finance, education, music, and extra. In our results, the first question we want to answer is how many apps leak data through login statements. We found in 5,000 apps, 200 apps is 4% with log-related 10th floor path, and 380 sources are referred. And these apps, some of them, they belong to the business, finance, and casino in the Google Play. And in the code libraries, we have the view of log in the Android apps. We calculate the source line of the code, the log line of code, and we use it to divide the source line of code, and we get the log density. And also we calculate how many logs in the exception block and how many logs in the reflective cause. We compare the apps, the good apps, and with the apps which has the log-related 10th floor path. And also we compare the apps in the different years to see the difference. And in the end, we get the average data for each of the column. And generally speaking, in 371 lines of code, there is one log statement. And around 26% of the log statement, they are in exception. Around 6% of the log, they are in the reflective. The most important value in these tables is the comparison between the good apps and the apps with log-related things. We find the good apps has a higher log density. It means it has more log in their apps, and also they have higher percentage in the exception than the apps with log-related things. One possible explanation is for these good apps, the developers are more experienced and they applied the good practice. They use a lot of log. However, before they publish their apps, they remove the log statement, which may leak the personal information. And they use more log to handling the exception and explain the errors. After we check all the 10th floor paths, we analyze what kind of information is leaked. We find around 186 network information, include the MAC address, device ID, SIM number, and extra. 22 location information, include the longitude, latitude, and the account and 2 account information, include ID and token. Then the 170 database information, include password and email. Here we don't put password into account because when we check this 10th floor path, we find the password value come from the database instead of the object account. So that's why we put here. Now I would like to give you some examples of our findings. For example, the first one is related to the password. In these apps, it's marked as business in Google Play and has 10,000 installation. As we explained before, here is one database query which search for the password value, and this value is given to the $4, and transfer to the function string A, and this function get this password value and give it to $1 and return this value in another function below A. So the password value is given to $3, and in the end, there exists one log statement which displays the password. The next case is related to the device ID. It's also in the same application. However, the process is more simple. We can say they use the get device ID function to get this information, and use the variables to receive it. And this value is transferred from $4 to $5 until $6. And in the end, there exists one log statement debug, which display the device ID. The next example is not as business, but it's named Moto File Manager. But I use it because it has around 10 million installation in the Google Play. Like the password, the MAC address is transferred between the $5 to $1, then become one part of the $7. Then the MAC address value transfer to another function belonging C, and inside the belonging C, the value transfer to another function belonging A as the third parameter. And in the function belonging A, there exists one variable $0, which takes the MAC address information and it's formatted to $1. $1 is displayed in the log statement debug here. So here is the MAC address transfer between these three functions and displayed in the log statement. In summary, we investigated the impact of logging practice on data leakage in 5,100 apps. We explored how come poor logging practice in the mobile applications, and we found 200 apps is 4% leak sensitive data, such as the passwords, email addresses, location information, device IDs, MAC addresses, and so on. For the future directions, because our results suggest the connection between the context of logging practice and whether these practices are good or poor, so we still need the further investigation to get more insights of this collection. Another point is automatically classify the leak data in the categories like the network, account, location, and database. And we need still continue the experiment with more apps, include the commercial apps from various categories to understand the scope of this problem. And we would like to design the technique to avoid this problem forever. So here is our publication on my thesis, and we still have another one which in preparation. So thanks for your listening, and all the questions are welcomed. Thank you.